Let's be real for a second. Taking a Cambridge physics exam is a lot like being a professional photographer. Think about it. A master photographer doesn't just point a camera and hope for the best. They have to find the perfect angle. They have to frame their subject to highlight the absolute key evidence in the shot. And right now, we're stepping into the shoes of the ultimate strategist for your Cambridge examinations, zeroing in on syllabus code 0625. We're going to tackle the fascinating and honestly often entirely misunderstood properties of waves. But we are not just going to sit here and memorize textbook definitions today. No way. We're undertaking a complete masterclass in decoding the exam command words. Let's look at the actual challenge you're up against by checking out two typical students tackling a real past paper. First up, we've got Alex. Now, Alex absolutely loves physics, but when an exam question asks about wave diffraction, Alex overloads the page with raw, unfiltered physics facts. We're talking a massive, dense paragraph about literally everything they've ever learned about waves, but providing zero actual analysis of the specific scenario in the question. And what happens? The examiner's red pen strikes right through it. Then we have Sam. Sam is constantly fighting the clock. Sam rushes, entirely misses the specific command word requirements, throws down a one-word answer when a detailed, structured explanation is actually required, and just like that, loses out on 3 incredibly easy marks. Today, we are going to transform those red pen marks into green check marks. We're going to build a system so totally foolproof that whether you're sitting the 0625, 0651, 0652, 5054, or 9702 papers, you are going to extract every single available mark.
Okay, let's dive into this. Here's our flight plan for today's explainer. We'll start with the exam code for waves, then move into calculating wave speed, describing wave behaviors, explaining complex scenarios, and finally, wrap it all up with the physics success blueprint.
Section 1, the exam code, waves. Let's understand the actual foundation of energy transfer. Before we can hack the exam, we have to establish what a wave actually is through the lens of a physicist. Here is your golden definition. A wave is a model used to explain how energy is transferred from place to place without transferring matter. I want you to lock that in. Write it down, highlight it, underline it. When the exam asks what a wave transfers, the answer is always energy, and absolutely never matter. Think about the sheer, mind-blowing scale of this concept for a second. Our source material brings up Albert Einstein's prediction of gravitational waves. Einstein hypothesized that the universe is made of this fabric called the space-time continuum. He figured that massively violent interactions, like two black holes literally spiraling into each other, would create tiny, incredibly fast ripples in spacetime. And guess what? A century later, scientists at the LIGO Observatory actually detected these exact ripples. Those gravitational waves traveled all the way across the universe, transferring absolutely immense amounts of energy, but they didn't drag the actual matter of deep space along with them. It doesn't matter if it's a cosmic ripple from a collapsing star, a seismic wave from a devastating earthquake, or literally just you splashing around in a swimming pool. The core principle is completely identical. The molecules or the medium itself simply vibrate. They move up and down or back and forth, passing that kinetic energy to their neighbor. The matter stays put, the energy travels. If you write that waves transfer matter on your exam, you are immediately dropping a mark.
And this brilliantly illustrates exactly how we study these massive, universe-sized concepts in a simple, controlled laboratory setting. Physicists use a ripple tank to model the behavior of light and sound. Looking at the top image here, you can see a straight wooden bar vibrating up and down on the water's surface. That regular motion creates equally spaced, perfectly straight ripples. These straight ripples act as an absolute perfect model for a broad beam of light, kind of like rays traveling from the sun in straight parallel lines. Alternatively, if we swap that bar out and use a tiny spherical dipper vibrating in the water, it creates these beautiful circular ripples that spread outward in all directions. This perfectly models how light spreads out from a single point source, like a lamp or a light bulb in your bedroom. It's an incredibly useful visual tool for your toolkit. When you see a ripple tank diagram pop up on your exam paper, you need to remember that the lines represent the wave fronts, which are essentially the crests of the waves all moving together in sync. The physical distance between each of those lines, that is your wavelength. Understanding how to read this visual model is the master key to unlocking the higher tier application questions later on in the paper.
Now we are getting into the absolute core strategy of this session. Take a close look at this text comparison straight from the course book's margin notes. This right here is where students like our friend Sam constantly lose their hard-earned grades. Let's break down the assessment objectives. The word describe means you literally just state the facts of what is happening. You give the characteristics and the main visual features. The wave slowed down. The wavelength decreased. That is a description. It's the what. But explain is an entirely different beast altogether. Explain requires you to set out the purposes or the reasons. You must make the invisible relationships between things completely evident to the examiner. You have to provide the why and the how, firmly backed by physics evidence. This is where the top-tier students use the PEEL framework that stands for point, evidence, explanation, link. If the exam explicitly says explain, and you pull a SAM and merely describe what is happening without giving the underlying physics reason, you're going to score maybe 1 mark out of a possible 3 or 4. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Section 2. Calculating wave speed. Let's transition into the quantitative, mathematical side of wave physics.
When you see the command word calculate printed on the page, the examiner is explicitly telling you to work out the exact answer from the given facts, figures, or information in the prompt. This is not a guessing game. It's not a place for vague concepts. It requires a highly specific formula, incredibly clear substitution of numbers, and a final answer wrapped up with the correct units. Remember our rushing student Sam. Sam will read a math question, punch some numbers into a calculator, and just quickly scribble down the final number on the answer line. If Sam makes even one tiny accidental calculator error, maybe pressing a 5 instead of a 6, they get 0 marks. Absolutely nothing. But if you frame your answer correctly and show your step-by-step working out, even if your final calculation is slightly off due to a button slip, the examiner can and will award you crucial method marks. Calculate is a strict demand for a beautifully structured mathematical argument.
Let's walk through a classic past paper scenario, very similar to worked example 14.1 in your text. Imagine an FM radio station is broadcasting signals with a wavelength of 1.5 meters and a frequency of 200 megahertz. We need to calculate the speed. Here is your bulletproof execution plan for guaranteed marks. Step 1. Write down exactly what you know on the side of the page. Frequency, denoted by F, is 200 megahertz. Now watch out, here is a massive trap. You absolutely cannot use megahertz in the standard physics equation. You must convert it to standard SI units. Mega literally means million, so that is 200 million hertz, or 2 times 10 to the power of 8 hertz. Wavelength, lambda, is given as 1.5 meters. We want to know v, the velocity or speed. Step 2. State the equation clearly for the examiner. V equals F lambda. Wave speed equals frequency times wavelength. Writing this exact formula down alone often instantly secures your first method mark. Step 3. Substitute your values into the formula precisely. V equals 2 times 10 to the power of 8 hertz multiplied by 1.5 meters. You are holding the examiner's hand and demonstrating exactly how you are arriving at your conclusion. This level of framing is the defining difference between an A and an A-star student.
And when you crunch those numbers flawlessly, you get 300 million meters per second, or written in standard form, 3 times 10 to the power of 8 meters per second. If you're a sharp physics student, that massive, incredible number should immediately ring a bell in your head. That is the exact speed of light in a vacuum. Radio waves are a key part of the electromagnetic spectrum, and a fundamental rule of physics is that all electromagnetic waves travel at this exact same speed through air or a vacuum. So, as a built-in cheat code, if you ever calculate the speed of an X-ray, a microwave, or a beam of visible light on an exam, and you don't get a number very, very close to 300 million meters per second, you know immediately that you've messed up and need to go back and check your working. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's jump into Section 3, Describing Wave Behaviors. What exactly happens when the environment changes?
Now, what's really, truly interesting about this ripple tank diagram is how perfectly it tests your visual data scan skills. I want you to treat this like a 60-second challenge. Scan this data visually. You have a ripple tank diagram showing deep water on the left side, transitioning to noticeably shallower water on the right, where a solid Perspex block has been submerged. Look really closely at the wave fronts, those lines representing the wave crests. If the exam specifically asks you to describe what happens to the wavelength, wave speed, and frequency when the wave enters the shallower water, what exactly do you write to get full marks? Remember the rule we said earlier. Describe simply means stating the characteristics based strictly on what you visually see without necessarily having to dive deep into explaining the complex molecular interactions behind it. So look closely at the distance between those parallel lines as they cross over the submerged block. What is the obvious visual trend happening right in front of you?
Time's up. Here are the precise, zero-fluff, descriptive bullet points the examiner's mark scheme demands to see. First, the wave speed decreases. Why does this happen? Because as the water gets suddenly shallower over that perspex block, the wave literally drags on the bottom, friction kicks in, and it slows down. This is the classic phenomenon of refraction. Second, the wavelength clearly becomes shorter. You can literally just see this in the diagram. The ripples visibly bunch up and are much closer together over the block than they were in the deep water. Third, and this is the ultimate, incredibly common trap where thousands of unprepared students lose a mark every year, the frequency remains completely constant. Let's do a quick find the flaw exercise here. Imagine our student Alex wrote, the wave slows down over the block, so naturally fewer waves hit the block per second, meaning the frequency drops. That sounds logical, right? But it would get a massive red cross from the examiner. The flaw is fundamentally misunderstanding what controls frequency. The frequency is determined entirely and solely by the source, the vibrating bar making the waves in the first place. That bar is still plunging into the water at the exact same unrelenting rate, sending out the exact same number of waves per second. Therefore, frequency absolutely cannot change just because the water got shallower. If you can nail that counterintuitive concept, you are truly thinking like a Cambridge examiner.
Section 4. Explaining complex scenarios. This is where we connect the why and the how with concrete evidence.
We are now going to explore the phenomenon of diffraction. Put simply, this is what happens when straight waves are forced to pass through a gap in a barrier. Look at these three diagrams pulled straight from your course book. In diagram A on the left, the physical gap in the barrier is quite wide. In diagram B in the middle, it's notably narrower. And in diagram C on the right, the gap is very narrow. Notice exactly how the shape of the wavefronts radically changes after they pass through that barrier. In A, they stay mostly perfectly straight, just curving slightly at the very far edges. But by the time we get over to C, the waves are fully spreading out in perfect wide semicircles. This visible spreading out of a wave as it travels through a gap or past an edge is the textbook definition of diffraction. It applies to water waves spreading into a harbor bay, sound waves bending around the doorway so you can hear someone talking in the next room, and even light waves creating a glowing halo effect in heavy fog. But the real challenge is, how do we properly structure a written answer explaining exactly when this diffraction is most pronounced?
This is exactly where you need to implement speed writing combined with that Peel framework we discussed earlier to absolutely nail an explain question. Let's look at item 1, a wide gap. The rule is, if the gap is much larger than the wavelength of the incoming incident wave, the diffraction effect is extremely minimal. The central part of the ripple just barrels right through and remains straight, and only the extreme edges curve. Now rigorously compare that to item 2, a narrow gap. When the physical width of the gap is exactly equal to or very closely matching the wavelength of the waves, boom, you get the absolute maximum spreading effect. The waves diffract entirely, forming strong, pronounced circular ripples that fan out into the space behind the barrier. If the exam asks you to explain this, let's use the framework. Your point is that the gap size relative to the wavelength is what dictates the level of diffraction. Your evidence is the specific visual difference between the straight ripples and the curved ripples. Your explanation is that maximum diffraction physically only occurs when the gap width matches the wavelength. And finally, your link explicitly connects that entire package back to whatever specific scenario the question asked about.
So let's put that to the test. Let's apply this directly to a high-level, complex exam question. The question reads, explain why a man living behind a mountain can receive radio waves with a wavelength of 1500 meters, but not shorter waves with a frequency of 100 megahertz. Notice the command word right at the start, explain. You cannot just describe the fact that he hears one broadcast and not the other. You must provide the underlying relationships and physics reasons. Let's do a speed writing challenge in our heads. Think about the mountain as a massive physical obstacle, acting exactly like the edge of a gap in our ripple tank from earlier. Remember the golden rule we just learned? Significant diffraction only happens when the wavelength is comparable to the physical size of the obstacle. A mountain is obviously huge. A radio wave with a massive 1500-meter wavelength is long enough to significantly diffract or bend right around the immense physical edge of the mountain and travel down into the valley to reach the man's house. But what about the other signal, the 100 megahertz wave? If you quickly calculate its wavelength using v equals f lambda, where v is our old friend, the speed of light, 3 times 10 to the 8th, you will find its actual wavelength is only about 3 meters. A 3-meter wavelength is incredibly, laughably small compared to an entire mountain. Because of this massive size mismatch, it will not diffract around it, it will simply be blocked or absorbed. That contrast right there, that is the complete, multi-mark, perfectly framed explanation the examiner is hunting for.
Let's look at one final, incredibly tricky command word before we consolidate our ultimate system. Deduce. To deduce literally means to logically conclude something from the available information presented to you. When you see deduce, I want you to think of yourself as a physics detective. You don't necessarily need a calculator for a pure deduction. For example, imagine an exam question shows a diagram of a wave traveling towards a sandy beach, and the text prompt says, "The sea is much calmer later in the day. Deduce the new amplitude of the waves." The available piece of information they handed you is calmer sea. The logical, evidence-based physics deduction is that a calmer sea inherently possesses less kinetic energy, and since we know that amplitude physically represents the energy level of a wave, the amplitude must therefore decrease. You use the provided context clues to infer a completely logical, physics-based conclusion. No heavy math required, just pure analytical framing.
Section 5. The Physics Success Blueprint. This is it, your ultimate, consolidated exam checklist.
So the absolute crucial point I want you to take away from this explainer is that understanding the raw physics concepts and understanding the specific language of the exam are just two halves of the exact same coin. Here is your ultimate cheat sheet recap. Take a mental snapshot of this. Rule 1. Waves transfer energy. They absolutely never transfer matter. Rule 2. The equation V equals F lambda connects speed, frequency, and wavelength, and you must always boldly show your mathematical working out. Rule 3. When a wave enters shallow water, it refracts. The speed decreases, the wavelength noticeably shortens, but the frequency is completely locked in and constant. Rule 4. Diffraction is the spreading out of waves, and the angle of that diffraction is greatest when the gap size perfectly matches the wavelength. And Rule 5, honestly the most vital rule of all, always decode and answer the specific command word given in the prompt. Do not just describe when the examiner asks you to explain the why. Do not try to explain when they are asking you to precisely calculate a value. Frame your shot perfectly. I'm going to leave you with this final, highly provocative thought. Are you just blindly memorizing thick physics textbooks, crossing your fingers and hoping for the best? Or are you actively mastering the command words to truly crack the Cambridge exam code? All that brilliant textbook knowledge is practically useless if you don't actually know how the examiner wants it structured and framed on the page. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. Subscribe right now to at acetheexams_IGCS and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. Keep studying smart. Take control of the exam language, and I will see you in the next explainer.